All right, we have chapter 15. This is all about exoplanets. These are, of course, planets that are outside of our solar system, which we've detected quite a few. So this is just a summary of what we're going to talk about. We're going to use the modeling of planet formation, mostly, the condensation theory. That's the one that we generally rely on. We look at solar system regularities and, of course, irregularities. Exoplanet detection, how do we find these exoplanets? What are some properties of them? And then we'll talk about, how different are the other solar systems that we've found compared to ours. And we always try to compare what we know to, especially with astronomy. If you know about something like, the Earth, we know the Earth, we compare the planets within our solar system to the Earth. Some of them are quite different, and so we make note of that. So let's get started. Right now we know about the thousands upon thousands of confirmed exoplanets. Okay, so these are, and we'll get to how we know about them in just a little bit. But confirmed is, we use telescopic information. And I'll explain that. Very few of these, 3,000, in fact, just a small handful, have been directly detected. We have other methods of indirectly detecting the planets. And then right now there's over 2,500 candidates, and this was several years ago. And nowadays, of course, there's many more. This number continuously grows as we detect more and more planets. One of the space missions that I'm going to talk about a little bit is Kepler, which was a groundbreaking mission. The current one is called TESS, and TESS is doing a great job of finding more and more of these planets. All right, let's get more into this. Again, the condensation theory, let's just go over that again. We did talk about this in chapter 6. So you have this large interstellar cloud. Now we find these in our galaxy, in other galaxies as well, where there's this huge cloud of mostly hydrogen that it exists between the stars. Somehow that cloud begins to, well, not just somehow. It's gravitation. Okay, let's face the facts. It's always gravitation. But let's say some star system, some other star passes by, and it gets this thing. It disturbs it gravitationally. Disturbs this giant cloud, which is a three-dimensional object that is, huge. It's many tens of light years across. Generally, they start out really large, but once this gravitational disturbance happens, or sometimes called a perturbation, once that happens, really we understand the physics of what happens afterwards quite well. As this thing contracts, gets smaller, it will begin to the overall cloud begins to rotate, and as soon as that happens, well not right away, but over the course of many millions of years, which in astronomy terms, millions of years is a relatively short time, the cloud will collapse into a disk, and so the reason that this theory, if this is the theory that works, we should see, when we look at other solar systems, disks of material that are relatively flat, that exist in a plane. And of course, that's what we find in these other planetary systems. Of course, they don't line up, in a nice manner. They're, some of them are at huge angles. When we look out at the different solar systems, their plane can be at any angle. That's pretty much random throughout the Milky Way galaxy. But the fact that the plane exists, that there is a plane which all this debris and planets go around their star is extremely important. All right, and of course this thing as it collapses, if it's going to become a star system, you have one or more stars that are born in the middle of this rotating cloud. The reason I say more is, our solar system, of course, just has one star in the middle, and when we look out at the Milky Way galaxy, our galaxy, it turns out that almost half of the stars, the star systems that we run across, are actually binary systems, or even mostly binary systems, where there's two stars that are orbiting each other, and then the planets will be orbiting those two stars. There are even more, systems that have three stars around them. In fact, there's a relatively nearby one nearby our sun, called the Alpha Centauri system. Alpha Centauri is the nearest star system to our sun, and there's actually three stars orbiting each other. That's just a little trivia there. All right, so again, we use this condensation model because it explains so much of what we see. So of course, as this all this gas and dust, again, mostly hydrogen and about 25% helium, as it collapses and forms a new star, you have planetary material forming, close by the star and then further out. The close by the star tends to be rocky worlds, at least when you look at our solar system, rocky worlds, and then the Jovian planets are further out. All right. So the condensation theory covers these different properties that we talked about in Chapter 6. For example, the fact that here, let me. Well, you can just look at the Chapter 6 videos to talk about, angular momentum, the conservation of angular momentum, and things like that we already discussed. But let's talk about the exceptions here. So there are several exceptions to note. For example, remember, one of the things that we find about Venus is, even though it's going around the sun in the same direction as all the other planets, its rotation about its axis is though it is upside down. It's rotating about its own axis in a clockwise manner, which we sometimes call retrograde rotation. And that's very strange. We really think that somehow two large bodies, collided or merged to eventually form Venus, and that's what got it rotating the wrong way, if you will. All right, so let's see. And of course the theory about how the moon formed, our moon, around the Earth, it involves a collision, a very massive collision of the early Earth with another planet that no longer exists in the early parts of the solar system, roughly the first billion years or so of the solar system, and that collision led to our moon. And there's also when you study Mars, there's a big difference in the northern hemisphere and the southern hemisphere in Mars, and we think that there was a huge collision on Mars that caused this difference between the two hemispheres. So these are irregularities. The regular stuff is the things that we talked about in Chapter 6. Also, of course, the planet Uranus is tilted by about almost 90 degrees. Again, a collision is more than likely responsible for that. I mean, we don't really have a way of explaining it, explaining that tilt, that 90-degree tilt, so that basically the North Pole and the South Pole are lined up with the plane of the solar system. How do we explain that? We theorize that there must have been a collision. One of the moons of Uranus has like 5 major moons. One of them is called Miranda, and of course it was named after one of the Shakespeare one of the characters in I think it's The Tempest. One of the plays of Shakespeare. And anyhow, that doesn't really affect the astronomy. When you look at Miranda, and close-up images of Miranda, which of course come to us from the Voyager 2 encounter in the 1980s. Here, let me go back. Hold on just a second. I didn't mean to do that. One of the things that when we look at Miranda seems to be had been completely destroyed or almost so, and then basically reformed. It looks like a pile of rubble when you look at the geology of it. Now let's see. We see also, remember, these are all irregularities. We see interactions between between Jovian protoplanets and the planetesimals that are responsible for some of these irregular moons. We also see some binary Kuiper belt objects. In fact, Pluto and its large moon Charon. Pluto actually has I think it's 3 moons. Might be even more than that now that we've detected. Anyhow, the Pluto and Charon happens to be really large compared to Pluto, compared to its host planet. Pluto's bigger, but Charon happens to be exceptionally large, for a moon. And we think that could have formed through collisions before ejection by interactions with the Jovian planets, with the gas giants. All right, so many of these explanations have one common thing: this catastrophic or almost catastrophic, almost completely destroying collision, right? Catastrophic would be the kind where these things are completely broken apart at one instant. And normally you don't, in science, you want to have an explanation for things that it's not like a one-time thing, right? Like a gigantic collision. However, we more and more as time goes on, the more and more evidence shows that's in fact seems to be the case with some of these irregularities that we find certainly within our solar system. So a lot of this stuff can be explained through very large scale collisions. All right, so let's talk about the spacecraft Kepler and the spacecraft TESS. And of course, let me go into, let's see, I'm running out of, these videos, of course, I have to, I only can do it in 15-minute increments, and it looks like I'm just about running out of time. But I want to talk about a little bit of the history. If you go back to the early 1990s, we really didn't know that there were other planets around other stars. We theorized that there were, but we didn't have any evidence of that. We